So what I'm going to show you here is the evolution of aerosols, which are little droplets that reflect sunlight back to space, and water vapor in the stratosphere after the Hunga Tunga eruption. And so you have aerosols in this panel, and you have water vapor over here. And this is altitude running from 15 kilometers to 40 kilometers of altitude. So this is the stratosphere, and this is latitude on this axis, running from 80 degrees south here. This line here is the equator to 80 degrees north. And this dashed line is the latitude of the eruption. And the colors indicate how many aerosols there are. Now, the instrument that measures this, the instrument's called OMPS, it's on the NOAA polar orbiters. It measures aerosols by measuring the light the aerosols scatter out of the atmosphere. And you can see this is what I would consider to be background aerosols. This is the aerosols that are just sort of always there. In the tropical lower stratosphere where this blob is, this is where air is entering the stratosphere from the lower atmosphere, and it brings up all this crap that gets aerosolized and turned into droplets. And so that's basically what you're seeing in this region right here. So this is January 1st, 2022, so let's let it roll. And there it is, you see background, and then boom, there goes the eruption. So let me stop it and just say, so the first thing you'll notice is you get a lot of aerosol from this eruption. Now, what you may hear people say are things like there wasn't much aerosol, and that's half true. There wasn't much compared to previous eruptions. So if you take an eruption like Mount Pinatubo in 1991, that volcano had a much bigger aerosol cloud. But still, this volcano injected enough sulfur that it produced a clear aerosol cloud that the satellite could easily see. And remember, the satellite's seeing this because this aerosol cloud is scattering light. So that's how they see it. So there was plenty of aerosol in the stratosphere. So let's let it run. And now we can see the aerosol evolve over time. And one thing you'll notice is the aerosol layer is slowly sinking. And that's because these aerosols are particles, and they sink under the force of gravity. And also the circulation of the stratosphere is down at mid-latitude and high latitudes here. So you'll see it's sinking back out of the stratosphere. Now let me stop right here. One thing you'll notice, you'll see at these high latitudes, these sudden appearance of these really thick aerosol. Now this is July, so it's winter time in the southern hemisphere. And the polar regions of the winter hemisphere get so cold that you actually condense water and other constituents, and you form these things we call polar stratospheric clouds. And that's what you're seeing. And these polar stratospheric clouds, which people refer to as PSCs, are one of the key components of the ozone hole. So you'll see these PSCs form in the wintertime. They'll appear, and then they'll disappear, and then they'll appear, and they'll disappear, and you'll see them flashing in and out of existence. And the instrument stopped working for a couple weeks, and now it's back. And you'll notice the aerosol from HT is slowly sinking. So now we're in September. You see PSCs are popping in and out of existence. Oh, and now I should say, now it's this is January, so it's wintertime in the north, and so now you see PSCs forming in the northern hemisphere. Now it's February, March, we're entering spring. And you see the aerosols are largely out of the stratosphere now. We're approaching the aerosol conditions that were there before the eruption, what I would call background levels of aerosols. And we may not be quite there exactly yet, but we're close. All right, so that's it. All right, so now let's look at water vapor. Okay, so this is the water vapor plot, and it shows it's very similar. This is altitude on this axis from 15 to 40 kilometers. This is latitude on this axis. So it's 80 degrees south here to 80 degrees north here. Here's the equator. Here's the latitude of HT. So let's run it. This is early January. And boom, there goes the eruption. So you'll notice the eruption injected a huge amount of water vapor. It's off the scale at about 26 kilometers of altitude. Now, unlike aerosols, which are little particles and kind of sink under the force of gravity, these water vapor are molecules. They don't really sink. And so instead of seeing the water vapor sink the way the aerosol layer did, what you'll just see it as the water vapor will just sort of slowly expand. And it will be pulled by the stratospheric circulation, and you'll just see it generally humidify the atmosphere. All right, and so you'll see water vapors kind of spreading around, following the circulation of the stratosphere, and it's just sort of expanding and moistening the entire stratosphere. So now we're in December. All right, so let me stop it here, and we can compare water vapor from January of 2023 with water vapor from January of 2022, and you'll notice that the stratosphere is much moister in 2023 than it was in 2022. And that's, again, just a consequence of all of the water that got injected, and then it slowly spreads out. And it looks like HT added, 4 or 5 parts per million to the stratosphere above about 25 kilometers. So now we're in February. So I'll just end it there. And so you see that the HT eruption added a lot of aerosols to the stratosphere, which stuck around for about a year. They added a lot of water vapor to the stratosphere, which is still up there. And the aerosols tended to cool the climate, and water vapor tends to warm the climate. And so the net effect of the volcano is the difference between those two factors.